So the rest of the lectures for today are meant to be a linear algebra review, pretty much. So if you remember things from Math 4A pretty well, then you can consider the rest of the lectures for today to be mostly optional, I guess. Maybe skip through and skim through if that's the case. If you don't remember 4A that well, or if you did not learn it that well when it was taught, then probably you would want to pay attention. So the first thing to be clear on is what is meant by matrix times vector. So a matrix is a grid of numbers, right? But it's a lot more than that. If it's just a grid of numbers, then it's nothing different from just a table, right? But what makes it different, what makes it a matrix, is that we care about how it acts upon vectors. So this is what it's all about, matrices acting on vectors. And the quickest way to explain what this is without gesturing and pointing all over the place to where different numbers are going to go is to say the result of this matrix acting on this vector is to take a linear combination of the columns. So this column and this column, 1, 3, 2, 4, and to draw your coefficients from the vector being acted on. So 5 and 6 are the coefficients. So that's the quickest way to really get what it is. And if you multiply two matrices, so you can multiply two matrices, look, maybe that. The sizes have to match for it to make sense. Actually, up here, the sizes also had to match. Since what you're doing is you're taking the green columns and taking a linear combination using blue coefficients, there have to be as many blue coefficients as there are green columns, right? So this vector has to be as tall as this matrix is wide. And similarly, when you multiply matrices, you're going to need a similar kind of compatibility. This one has to be as tall as this one is wide. So here in the example, I'm showing you 2 by 2 and 2 by 2. Everything is 2, and so it matches. But what matters is that these inner dimensions match. This one is how tall this is, and this one is how wide this is. So when we describe the dimensions of a matrix, we're always giving the number of rows and then the number of columns. So what does it mean when you multiply two matrices? Well, it basically means do this, but to each column of the right-hand matrix. So first do it to this column, and then you get so first act using this matrix, act upon this column, and you get this linear combination here with these chosen as the coefficients, and then go ahead and do it with this column, so then you would get this with these coefficients. Right? So this matrix on the blue is this matrix on the red is this, and then make those the columns of your new matrix. So here's a new matrix. This shall be the first column of the new matrix, and this shall be the second column of the new matrix. So this thing, if you compute it out, is a column with 2 entries. This thing, if you compute it out, is a column with 2 entries, and if you package them together, like this, horizontally arranged, then you get a 2 by 2 matrix, right? This is vertically 2, this is vertically 2. Then you put them next to each other, and you get a 2 by 2. So that is the idea with multiplying two matrices together. And all of this can kind of be summarized if one just writes down a formula. So if I have a matrix A, then I can write subscripts like ij for what I would call the ij entry. Which is the thing that is in the ith row and the jth column. And then if you have a column vector, like v is a bunch of stuff, then in order for AV to make sense, we would need v to be as tall as A is wide, right? So we need the number of rows in V, or the number of entries in V, to be the same as the number of columns, or the number of possible j values for A. So let's call this V sub j is the jth entry of the vector V. Then when we say A acts on V, what we're saying is a new vector whose ith entry is going to be the sum of aij vj running over all j from 1 to however many j's there are that you can possibly run over. So from 1 to whatever is supposed to go here, however tall this is or however wide A is. And then if you want to describe multiplying two matrices together, like A, B, then that would be the matrix whose ij entry is going to be, maybe I should say ik entry, whose ik entry is the sum over all possible j's from j equals 1 to whatever is the tallness of B, also known as the wideness of A, the number of rows of B, the number of columns of A. And this sum will be the ik entry of the product matrix. So this sort of defines for you the product. All right, but this is all great for calculations, and if you need to prove something, or verify that something works where the matrices can be of any possible size. But for us, for most of this section, we're going to work with 2x2 matrices. And personally, I find this kind of way of looking at things to be sufficient for most purposes. Definitely it will be for this portion of the class. So one important thing to pay attention to with matrices and algebra, when you're doing algebra with matrices, that is very different from doing algebra with numbers, is the multiplication is not commutative. So AB is not always the same as BA. And if you think about it, so what is meant by AB and what is actually meant by BA? So if a matrix is sort of determined by what it does to vectors, if you interpret it in terms of how it acts upon vectors, then when we say ABV versus when we say BAV, different things are being done to vectors in these different situations, right? This one says do B to V, then do A. This one says do A, right? You kind of read it from right to left, since you apply matrices from the left. So it's a little bit backwards the way you read it. This one says do A to V, then do B. And these could, doing them in different orders could result in different vectors, right, depending on what it is you're doing. If what you were looking at are numbers rather than matrices, then what you're doing is just scaling, right? So yeah, scale by 2, now scale by 3. Well, that's just scaling by 6. Scale by 3, now scale by 2. Well, that's also just scaling by 6. So there's no problem there. If you have 1 by 1 matrices, you're just scaling. But if you have 2 by 2 or higher matrices, it's going to matter, right? So just to show you an example, I've opened Inkscape here, where I can draw a picture, and I'm just using Inkscape because it lets me put in a matrix, what matrix I want to use to transform all of the pixels in this picture. So I drew this smiley face, which has an eye patch so that you can see, the eye patch is on one side, so you can see when it gets flipped around, which might happen depending on what I put in. So here ACBD, well, okay, I think this is just the 2 by 2 matrix that I'm going to end up applying. And you can think of the origin, so you can see the measurement here is 0 and here is 0, so the origin is right there. So you can think of like the eye, for example. There's a vector going from the origin to the center of the eye. Whatever matrix I put in here will get applied to that vector, and that will be the new location of the eye. And same goes for every other part of the picture. The new location will be determined by applying the matrix here to the picture. So you can get a feel for what a matrix does. So right now it's the identity matrix, so if I select this and I apply the identity matrix, nothing happens, right? 1, 0, 0, 1. But let's say I do this, put 1, 1, 0, 1. This will be a shear, so it gets sheared like that. And now let me go ahead and apply a rotation. So how about I do 0, 1, minus 1, 0. That'll be a 90-degree rotation. Okay, I have to select it. Apply. Okay, so it ends up like that. So if you do a shear and then do a rotation, so then rotation matrix times shear matrix, since it's written kind of backwards, results in this kind of thing happening to the original smiley. So let me keep that. Okay, so I've reset the smiley back to its position, but I kept the distorted one here so we can compare the end results. So now let me get this back to identity, make sure that I understand what I'm putting in. So now when I apply it, nothing happens. Good. Now let me do a rotation. So the same one I did before was 0, 1, minus 1, 0. So apply that. There's our rotated smiley. Now apply the same shear I applied at the beginning. So that was 1, 1, 0, 1. Okay, so now let me apply that. And we end up like that. So if you do a rotation and then a shear, you get this at the end. If you do a shear and then a rotation, you get this at the end. So the lesson is these two are different. So these are the two transformation matrices that I used. I think this smiley over here was the result of doing the rotation and then the shear, right? The shear was last. So this smiley over here was the result of this. First rotate, then do the shear. And then this smiley over here was the result of shear, then rotate. So these are not necessarily equal, and we are seeing they're not equal. So by the way, speaking of rotations, for example, how do I know this is a rotation? How did I just know that? So if you want to visually interpret what 2 by 2 matrix is doing, 0, 1, minus 1, 0, say, a good way to do that is to take advantage of the linearity of the whole situation. When the matrix acts on vectors, it does so linearly. So if you know how it behaves on a basis of vectors, then you can linearly sort of extrapolate how it must behave on everything else. And that lets you build a picture very easily. So here's what I mean. If you apply this 2 by 2 matrix to like C1 V1 plus C2 V2, then you get the same thing as if you did C1 and then the matrix applied to V1 plus C2 and then the matrix applied to V2. Now, if you choose a certain V1 and V2 that are a basis for the plane for R2, then you can basically know only what this matrix is on V1, what it is on V2, and then you can determine what it does to everything else. That helps you build up a picture. So let me use the standard basis instead of V1 and V2. So the standard basis means these vectors, 1, 0, and 0, 1. These form a nice basis. We will, in this course, have a need for other bases often, but this is a good basis for drawing pictures if you just want to quickly draw a picture. And let's see. So here, this is C1, and then let me use green for the result of applying this. What happens when I apply this to 1, 0? If you do it, you should get 0 minus 1. That's actually, you don't have to do any fancy calculation there. Just remember that the idea when you're doing matrix on vectors, you just take a linear combination of the columns and you're drawing your coefficients from the vector that's being acted on. So over here, 1, 0, you take a linear combination of these two columns, 1 times this plus 0 times that. So you just get this, 0, negative 1, plus C2 times, and then this on this, so 0 times the first column plus 1 times the second column. I just get the second column. So if you take any vector, any linear combination of 1, 0 and 0, 1, and you apply this to it, you get just the same linear combination, same coefficients, just change who you're taking a linear combination of. 1, 0 becomes 0 minus 1, 0, 1 becomes 1, 0. So we can fully understand what's going on if I just see how the blues become the greens, right? So here's one of the blues. Which green does it become? It becomes 0 minus 1. So 0 over minus 1 vertically. So the blue becomes this green. This blue becomes this green, right? So we can think of it as this got moved there. And then the 0, 1, this is 0, 1. Maybe I should really have 4 colors, but whatever. 0, 1 becomes 1, 0. So it becomes this. So it kind of got moved like that. So you see how it's a 90-degree rotation? Okay, so the camera's kind of flipped, but I'm not going to try to gesture. But you see how, but I just point, you see how it's a 90-degree rotation like that? Since the point being made here is, since these two blue vectors are just getting moved down to these two green vectors, they're getting rotated by 90 degrees, so does everybody else. Since when you apply this matrix to anybody else and a linear combination of the two blues, you're just going to get the same linear combination, but now of the two greens. So this is a really great technique for trying to visualize what a 2 by 2 matrix is doing.